Consider the complexity of Heapify. So what we want to do is that our input is a set of n keys, and these are unordered. Okay, so we're not making any assumptions on what the input is like, and we want our output to be the same n keys arranged as a heap, right? Now if you remember the heap property, and so we have this notion of either a min heap or a max heap. So for this, let's sort of make an assumption that we are dealing with a max heap. The basic argument of the proof does not really change, and nor would the algorithm, right? So let's make our life a little bit easier. So remember, as a heap, we assume that we have it arranged in a balanced binary tree. So let's start off with that assumption. So we have a binary tree. I'm just sort of drawing this out here with 8 entries. So this would be 1, and then again, and finally our root. Now this is our entire heap, so these are all our n keys. Just for convenience sake, what I'm going to make an assumption here is that the height of our tree is h, okay, and so at the finest level we're going to have 2 to the power h keys, right? The one level above that, you're going to have 2 to the power h minus 1, all the way till we have exactly 1 key at the top. So the total number of keys that we have in this case is going to be n, right? Which is going to be equal to the sum of all the keys at all the levels. Remember, this is not a recursion tree that we are drawing. This is an actual binary heap that we have. So, you know, even this key, for example, is a valid key, right? So the total is going to be the sum of all of these, which is going to be 2 to the power h plus 1 minus 1. Okay, so keep this in mind because we'll come back to this. Now, let's think in terms of what is the procedure. Since we are saying that we have a max heap, effectively we're going to sort of proceed in a bottom-up fashion. We're going to look at all the keys, and we're going to make sure that they are satisfying our heap property. And in this case, basically, since it's a max heap, we want to say that if you have the parent and we have 2 children here, the parent, let's call it P, and let's call this C1 and C2, then the max heap property is that P is going to be greater than or equal to C1 and greater than or equal to C2. We don't necessarily have a relationship between C1 and C2. And so this is a property. Now let's see how we could enforce it. So start off by considering the lowest level of the tree, 11, okay? So this has 2 to the power h keys, but if you consider any of these nodes, say this one, do we need to do anything about the maintaining the heap property? No, because it has no children, so it is fine. So basically, we do 0 work at this level, okay? Now consider the next level. Let me actually copy this guy so that you will be able to see this. Okay, there you go. And there. Okay, so let's keep this in mind. So the lowest level, the amount of work we did, and I'm going to sort of write the work in terms of 0, okay? Now, consider the level just above that. At this level, these are all my nodes, right? In order to ensure, how many we have? We have 2 to the power h minus 1. If you consider any of these parent-child relationship, the parent could be greater than either of these two. And so how many times would I need to push it down? I would need to push it down exactly once. So if we have 3 of these, I'm basically going to take the minimum of the 2 children and I'm going to replace it with a parent. So effectively, for each of these 2 to the power h minus 1 keys that I have, I could do 1 swap. And that's the amount of work that I do at this level. Now, if you, in the same vein, if you kind of consider these guys, right, then I have 2 to the power h minus 2 of these, and these can be pushed once, and twice, right? So for each of these, we'll have 2 possible pushes down, right? And so if you sort of generalize this summation, you'll see that, remember that we had a previous one of 2 to the power h times 0 plus this, all the way until the top, where we have a single key that can be pushed h times. Okay, so that's what we want to do. So effectively, we can write this series in a convenient fashion as summation j is equal to 0 through h, right? 2 to the power j times j, right? This is how we have written this, sorry, j minus h minus j. Oops, let me mess this up. Let's actually write it a little bit differently. Let's say it's j times 2 to the power h minus j, right? H minus 1, h minus 2, all the way until the end where j becomes h, and this you're getting a 1 here because it's 2 to the power h minus h, which is 0, so 2 to the power 0 is 1. So that's what we're getting. So now the problem is that how do we actually figure out this sum? Now, we haven't seen this before, but just for a second, let's sort of go back to our standard infinite series. So let me do this in a different color. So we want to do summation, and now I want you to do j is equal to 0 through infinity. So this is an infinite series that we are summing for x to the power of j. Okay, now it's an infinite series, and we are doing it for x is less than 1. So it does converge in this case. So basically we are starting off with a number that is less than 1, and we are taking progressively higher powers of it. So it does actually converge because each number is progressively smaller, and this sums up to 1 minus x. Okay, and you can go back to the earlier document that I have for the geometric series, and you can read up about this, right? This is a geometric series in this case. So now this is our sum. Now of course this is a little bit different from what we have out here. So because we have sort of like 2, if you take x is equal to 2, or in this case, or x equal to half, then you can do it. But what do we see out here is that we need to take the derivative of this one. So if we take a derivative, what we're going to get is summation j is equal to 0 to infinity j x to the power j minus 1 is equal to, what is the derivative? It's going to be the power. So this is basically equal to 1 minus x to the power minus 1. So that's going to be minus 1 times, you decrement the power here, so that's going to be 1 over 1 minus x square. And you have to take the derivative internally, so the derivative of 1 minus x with regards to x is going to be 0 and minus 1. So this is basically 1 minus x square, right? Now what we can do here is that we can multiply both sides by x. So what do we get? In this case, we are going to get, if I get to this part, we're going to get summation of j is equal to 0 through infinity j x j is equal to x by 1 minus x square. Now let's put x is equal to half, which if you remember is less than 1. So then we're going to end up with summation j is equal to 0 through infinity j x, sorry, let's put this thing. So 1 by 2 to the power j is equal to 1 half by 1 minus 1 half square is equal to half by 1 over 4, and this is equal to 2. On the left you see it's basically summation j is equal to 0 through infinity j by 2 to the power j. If you remember, this is what we initially wanted to do. So if you go back here, you see that this was our expression that we were interested in doing. So let's sort of go back So see, this is what we wanted. Now let's simplify this one a little bit. You remember that I can take this one, summation j is equal to 0 through h, j 2 to the power h 2 to the power minus j, and this is equal to summation j is equal to 0 through h, j 2 to the power h by 2 to the power j. We can take the h out because the summation is only on j, so we get 2 to the power h summation j is equal to 0 through infinity j over 2 to the power j. Now this is where we look at it. You see this one? Oops, I made one small mistake. We don't really have this as being infinity yet, right? But you see that this summation is very similar to the one that we just proved. And so basically we can write this now as an inequality, that this is less than or equal to 2 to the power h times 2, because you know this is going all the way to infinity and this is just a few sums, right? And so this is less than or equal to 2 to the power h plus 1, right? And so this is basically order of n, because if you remember, n was 2 to the power h plus 1 minus 1. And so basically that is your proof that Heapify can be done in big O of n. Okay.